Solidigm is launching 122 terabyte D5-P5336. I've only got the PS1010 and the 1030, and I really wish that I had the 122 what is happening? 122 terabytes? Well, look at that. It's Alan.
Hi.
Okay, so this drive is going to benchmark differently than you expect, and we need to talk about it. All right, chat. You don't know enough about modern enterprise SSD engineering because look. This thing is 122 terabytes. It's 2.5 inch. It's a 2.5 inch drive. Now it's a tall 2.5 inch drive, not like the 2.5 inch drives you may be used to. Maybe you work in the enterprise. Maybe you're used to SATA. It's NVMe 4 Gen 4 lanes, but I hold in my hands 122 terabytes. This is a density of data that mechanical hard drives right now, presently today, cannot touch.
Surprisingly light, too.
Yeah. I mean, a mechanical hard drive is 27 terabytes maximum. Yeah. You'd need 4 of them to match this capacity. Okay, mechanical hard drives, they're sampling 40 terabyte drives. Mm-hmm. So the enterprises, Amazon, it's like, oh yeah, 40 terabyte mechanical hard drive. That's the best they can do. They might be able to get to 100 terabytes by 2030. This is 122 terabytes. This enables 4 petabytes in 1 U of rack space.
Yeah.
That is insane.
It is.
But it also required a lot of engineering because Solidigm announced this in November, but it's only just entering general availability right now, today.
Yeah.
May 20th.
I mean, it takes time to fully cook these things. Yeah. We knew we could do it. It's just now we're actually doing it and shipping it, and you have a review unit.
Yay! I have to send it back in a week, though.
Well, that's okay.
But it is because it's like, $30,000 of equipment or something.
I don't think they cost that much.
It's $1,000. Yeah, it's probably, I don't know. It's not, it's like a generic pricing placeholder. I don't know.
Yeah.
So
we got to do things a little different when you get this big.
Yeah. Okay. So like the 1010 and the 1030, this is more engineering like we're used to. Mm-hmm. And, the first and most common misconception that we've covered a lot on this channel before is like the DRAM cache. These have DRAM on them. Yep. And there's stuff in the DRAM. And so a lot of people naturally assume, it's like a mechanical hard drive where it is. No.
Nope.
It's metadata. The DRAM is not used for your data.
Correct.
The DRAM is used for bookkeeping about what's going on with the flash media.
That's the biggest misconception. I run into it all the time, right? There's literally zero user data goes into the DRAM on an SSD.
Yeah.
Ever. It's just not what it's for, right? Not only that, it's actually, the DRAM is technically slower than what you are actually getting as a net effect. Because when you do a write to an SSD, there is an SRAM input buffer on the NAND chips. The actual die.
And the more NAND chips you have, the wider it can spread that.
And that's SRAM. That's faster than DRAM, right? So when you go to do a write to it, it goes across the bus. It passes basically straight through the controller, right across the channels to go out to the NAND. And then it goes into the SRAM input buffers. That's why when you do a QDEF1 random write to an SSD, the latency is like super, super quick. And it's as long as the load is not so high that you're bogging down the NAND and it actually has to try to play catch up, right? You get Optane level, random write latencies to the NAND, right? Because you're only the time as far as the host is concerned is just how long did it take to get into the buffer, and then the host, from its standpoint, it's done with the I/O, right? And then the SSD obviously has to do a little bit more work for the next little bit of time in the background, right?
And part of that is the magic of the flash media and everything else, because it's also correct to say that flash media writes are incredibly slow. Mm-hmm. But if you prepare the media to receive a write, then it is not actually slow. And the engineering with power loss capacitors and everything else ensures that the things that make it to that buffer actually make it to the media.
Yeah.
So you're guaranteed not to lose information. And that is hard-won engineering knowledge over 5-6 generations of storage.
Yep.
And so, writes. Reads are, that's why reads are slower also. It's like you have to do all of the mechanical
you have to wait.
stuff.
It has to actually get the data for you and deliver it before it can say that it's complete.
Yep.
Whereas for a write,
it can say that it's complete.
It's complete just from the standpoint of the host to the SSD, to the actual, to this connector right here. That's, that transfer is complete. It's on the SSD to figure out the rest of it.
The engineering of the inertia of that write is going to carry it through to be written, even if the drive loses power.
Yeah.
Which is amazing. That's a lot of engineering.
Yeah.
So DRAM, like keeping track, like say these are 8 terabyte drives, you can expect, rule of thumb, you would have 8 gigabytes of DRAM?
Yeah, there's in the industry they just refer to it as a 1-to-1 ratio, even though it's technically like 1,000 to 1, right? It's 1 gigabyte of DRAM per 1 terabyte of NAND. So that's your typical 1-to-1 ratio. It also applies to the client SSDs as well, right? If you have an SSD that has DRAM, M.2, whatever, in your regular desktop system, chances are it's a 1-to-1 ratio, just like that. And for the same purpose, too, even though it's client versus data center, same exact use case, the thing called a flash translation layer, which is this big table, metadata table that keeps track of, okay, sector 1 translates to which address of NAND. And that's got to be stored somewhere. That's the table. That's what the DRAM's for.
That makes sense.
Yeah.
But then when you have 122 terabytes of storage, that becomes problematic from a cost standpoint. And as we were discussing earlier,
128 gig of DRAM would be
Yeah.
a little crazy.
yeah,
right?
so that does not have 128 gigs of
No,
DRAM.
it does not. It has 16 gig, which, as it turns out, is more than enough, especially when you consider the use case, the expected use case of a drive like this, where you're just looking for the absolute maximum amount of capacity. Versus something like a PS1010, which you're looking for more on the lines of, this is one of the fastest performing drives on the market right now for NAND, as far as NAND goes. So fire-breathing drive, well, there's these concessions you have to make to jump from 8 terabytes to 128 terabytes.
Yeah, a lot of really interesting things washed out in the benchmarks with that. But we were talking earlier, and also I was surprised. I was like, oh yeah, power is a constraint. That didn't even enter on my radar thinking about it. But then it's like, oh yeah, that is kind of obvious.
Right. Yeah. It's and it really is a very much an independent. It depends. Right. There's different. It's not like an SSD just draws whatever its max is going to be when you do any particular thing. It's actually workload dependent. Right. So the peak for a drive like this, or actually most of the data center drives, if you do something like a 70-30 mix random or a 50-50 mix random, that's around where you're, the SSD's doing as much as it possibly can in that case, and that's where you're going to run up against your peak. And so, it's not very commonly known, but me as a person who benchmarks the crap out of these things on a daily basis, there's a lot of dials and tuning that has to go into that. So a drive like this, even though it's only 7.68 terabytes, is actually riding the 25 watt max of the
All the time.
No, not all the time. So if you just do like sequential reads, nope, you're not doing it.
Oh, that makes sense.
Sequential writes, probably not. Even like for some cases, it might not even be at the max for something like when this thing is doing its 3.3 million IOPS for random reads. It's actually not at 25 watts. It's as soon as you start mixing in some writes, and now you're trying to do a lot of things at once, and now it actually starts running against the max. And if you try to get higher than a 7.68, so if you have like 15 terabyte drive, we actually have to start pulling back performance intentionally in order to maintain, that 25 watt max.
That's really nice that the enterprise is a lot more serious about staying within those power envelopes, because in testing like consumer M.2, there's one in particular I can think of off the top of my head that it's like that's a 12.5 watt specification, and it has excursions to 15 watts all the
They're
time.
more like guide wines. It's a parlay. It's like, yeah. Well, yes, client tends to push it sometimes. It varies from manufacturer to manufacturer. Some of the data center guys do that too. I won't name names, but sometimes they get a little cheaty. It also depends on how granular you want to be with how you're measuring the power consumption of the device, because if you measure like down to the millisecond of power consumption, everything is technically going over the spec.
Yeah.
It's that the rating of the connector, because what that power consumption rating is based on partially is like the pins, how much current per pin is it rated for, and there's these sort of different ranges of like, okay, well, how do you actually measure that? Is it an average over how long? And it's, typically like either 10 milliseconds or 100 milliseconds, so like about a tenth of a second rolling average. Okay, don't exceed 25 watts for that. And depending on where you look and which spec, you'll see different time frames for what that window is, right? We ran into this back at PC Pearl when we were measuring, what was it, the AMD, 6 something, I forget what it was. The one that was like going over.
Oh yeah.
back in the day.
Yeah.
And like, if you measured it a narrow enough time, it was like double the rating. And it was like, no, that's not how you're supposed to measure it. You actually have to like average it out a little bit. But yes, there are limits.
It had crazy connector heating for 200 milliseconds.
Right. Well, and there's also, we've got to remember, like, Supermicro is making an enclosure for, to hold 24 or more of these, potentially 40. It depends on what the chassis design is. But, they're going to design their backplane. You can't just willy-nilly go to 30 or 35 watts with all of the drives. You're just going to, you're going to overload the backplane, right?
Yeah.
Yeah.
Well, that actually leads me into our next thing, where it's like these are U.2, and this is great. So this is like bulk storage U.2, and it's fabulous. But also there's E1 and E3, this is a different kind of connector. This is more designed for hot plug. This is designed for better power delivery.
Yep.
And there are some variations of this that support up to 40 watts instead of 25 watts of our U.2 companion.
Yeah. There's an E3L, which is just a little bit of like adds another inch onto the depth of this guy. And I think for the E3L, it's even supposed to be like a thicker.
Thicker, yeah.
Yeah, it's like a thicker enclosure as well. But same little tiny connector on the end, which is the same little tiny connector as that.
This is E1, so this is not E3, but this is E1L, and this is an older specification. But you can tell that they were preparing for that level of heat dissipation because it's heat sinks. It's a heat sink sandwich, basically.
Yeah, the whole thing's a heat sink.
This was first called like the ruler format. But they were planning, specification planners were planning on more PCIe lanes, potentially. There's a version of this connector that's 16 lanes wide.
Mm-hmm.
It doesn't look a lot different than the OCP3 connector. Oh, I mean, it's different. But and then the heatsink for power dissipation. And there are prototype versions that even go beyond 40 watts. But 40 watts is basically what is standard-ish.
That's super early because this is too thick.
Yeah.
Like, that's not like the E1 thickness now is supposed to be like, oh my goodness, it's like a third of that.
Yeah. Oh, unless you're CXL. CXL is still the old.
Yeah. Now for the E3S though, these are a little tricky as someone who tries to benchmark these things typically in a standalone like workstation style open test bed.
Yeah.
No, these things want linear feet per minute of air. Like this is the other designs. Well, that's a bad example. There's heatsink fins sort of built into the U.2 on many of them. There's some sort of, there's another drive over here. It's got like a little bit of a heatsink on it. Okay. So clearly they're going for more surface area, even though this is only up to 25 watts. This guy, if it was only an inch longer, could go to 40.
Yeah.
And there's just no room.
Nope.
Like if you ever open one of these up, sometimes they're even a sandwich of a couple of PCBs in here, and there's nowhere to put any additional surface area. So yes, you absolutely, like when I try to test these in an open test bed, like on a desktop or just like a open frame sort of a thing, I have like 3 fans pointed at the thing, and I'm even like taking masking tape and making a little duct so that the fan is literally like pushing air down both sides of the drive.
I have some PCIe adapters that are more heatsink than PCB, and that is very, very effective at managing those for benchmarking and everything else.
Yeah, you have to get the heat away from them somehow, and especially that's 25 watts. That's a lot to be just 2 flat surfaces like this, right? It will cook if you just put it in stale air. Yeah, so all these drives are 1-to-1 DRAM to NAND. I mean, that one is, but it's an old Intel drive. But yeah, once you get up to around 16 gig, it becomes less practical to keep throwing more DRAM at the drive. Number one, for cost. Like, this would have had 128 gig of DRAM. That's just ridiculous.
That's going to eat all your power budget, too.
The power budget's actually the worst problem than the cost problem. Because you get to the point where you're sucking up so much power just to keep the DRAM running. Number one, not great for economics. Like, this drive is meant to just be more along the lines of a mass storage with better latency than hard disks, right? And obviously better speed, but still within reason. You're trying to just cram a lot of bits into a particular space for a given power budget. You don't want to have most of your power budget being eaten, especially idle power budget, just keeping DRAM hot.
Yeah,
that's just ridiculous. And also, 128 gig DRAM would be so much power budget that it would actually reduce the overall performance of the NAND of this drive, because we would have to cut back the performance to make sure that the whole overall thing doesn't go over 25 watts.
Everything is a balancing act.
Yes.
that explains some of the stuff in the benchmarks and some of the stuff in the drive specifications. I mean, this is a PCIe Gen 4 drive, and we're talking about upwards of 7.5 gigabytes per second read, and what was it, like three?
It's around 3, yeah.
3 gigabytes per second write, and that's all power budget limited.
Yeah, the 3 for QLC media in a data center drive with no SLC cache, 3 gig per second is actually pretty good.
Yeah.
To get to. It seems low. You would say, it's only, there's Gen 5 drives now. They could do 14 gig per second. Well, number one, none of the Gen 5 drives are writing at 14 gig per second. They're doing, like for all the data center drives, they're doing around 10-ish. But, this drive is only 3, but it's a third of what the TLC drives are doing, but it's trying to store twice as many bits in a cell. So it's doing a lot more.
Safely, reliably.
Yes, safely and reliably, yes.
Yeah.
And part of that is down to, you have to realize where the pedigree from all the Solidigm stuff comes from. It comes from all the way back at the Intel days. Intel being the guys that were doing the floating gate NAND, they decided to go that path. Floating gate was better at more precisely storing, voltages within the cell than the competing solutions that have been up and coming. That's what the trade-off was the whole time, right? You saw the Samsung drives and all the other competing drives. They decided to go to charge trap NAND. That's what's in basically everybody else's drives. And yes, if you make a TLC drive out of that, it goes faster. You get better performance, right? It's actually what's in this drive, because the Solidigm PS1010 and PS1030, they're coming to us, via SK's like engineering team. So we have some of, that's the benefits of Solidigm working alongside of SK, is that we get sort of the
you can
best
build
of both.
SSD horses for courses.
Yeah, we could, build the more appropriate, choose your own adventure media, which one is the better thing for the job. But for this, floating gate is still kind of the dominant one there, because it can more quickly than charge trap and more reliably store a much higher precision voltage level, which lets you get away with, QLC media and fit that many crazy amount of bits into something that small and still have the performance be reasonable. Right?
And do the 5-year warranty, and to do the absurd drive endurance ratings.
Yeah, the endurance is now this endurance drive writes per day wise is not going to come anywhere near what the 1 or 3 drive writes per day of the fire breathing performance kind of drives.
But right? QLC, it's good for QLC.
It's QLC. Also, it's really hard to burn that out anyway, because it's 122 terabytes. How many drive writes per day are you possibly going to be able to pull off to that thing? And also, that's not really the intended primary usage, right? This is more along the lines of backing store-ish type of things. There's AI workloads that will, if you're working on a huge data set, gets spit out of all the GPUs, and then it needs to get laid down somewhere that can be accessed randomly quickly later, if it's like a RAG database or something like that, right? So given that the write workload tends to be sequential, and then the read workload is random, that's actually like the perfect sweet spot for this, right? Because the QLC likes to be sequentially written, because it's going to perform, it's basically going to give you its best straight line speed. Any SSD likes to be sequentially written, but especially QLC, which has more of a penalty if you try to do like a SQL database or something, crazy small random write.
70-30 mixed workload was still very good on this drive.
Yes, yeah, it's still going to do well on that, because 70% of it is reads, so it's still going to be okay, because it can handle just 30% of the writes.
That's more real world.
Yes, it is. But especially for the AI thing, it's a very lopsided, like there's not even good SNIA equivalent, like standard equivalent workloads. The AI thing is kind of throwing a couple of decades worth of SSD, testing knowledge and assumptions on their head, right?
No, AI changing everything?
Well, because for a typical data center type of workflow, it's almost like thou shalt do the same thing reads that you did writes prior. It's like the expectation is that they're always matched. So if you're going to do a 4K workload and 4K benchmarking, you have to have come back earlier and do the thing called preconditioning and got the drive all the way out to a steady state performance at 4K random writes, which is not what that drive would see, and that there's legit real world workloads that there's something like sequentially fill the drive halfway and then randomly read from it, and what is the performance of those random reads. Yeah, that's just the thing that almost never happens normally in any other prior sort of workloads in the industry.
That was also one of the engineering challenges with this that sort of ties into the internal structures and how it's managing things internally.
Yeah,
is that if you look at 4K random writes versus 16K random writes, the performance is basically identical, and the reason for that is internally this has what
well, do you mean 16 and 32K?
Or 16 and 32K.
Yeah. So there's a thing called an indirection unit size, which is, okay, if you only have so much DRAM, that FTL table can only be so big, metadata, you'd only hold so much metadata, and then you can always just do this sort of reverse math on it, right? If you start from your 1-to-1 ratio, and then you can work backwards from that. So given that this has 16 gig of DRAM on it, you do a calculation that works out to a 32K indirection unit, which is called IU. That means that the table only has a resolution of each entry in the table points to 32 kilobyte chunk of NAND, right? That's how that plays out. Now the pages in the NAND on this drive, since they're QLC and it's NAND that's designed to hold more data, like the page size has to get bigger. So I'm pretty sure the page size on this guy is 16K. So the IU size, even though the DRAM is technically, not ideal compared to a fire-breathing high-performance drive, 32K is close enough to the page size to where it's basically negligible difference because of that.
In random I/O, you're not going to pick the same sector twice.
Yes, true.
Which is where you might have a penalty.
Yeah, and also you don't expect the workload that this drive would see to go much below 16K anyway, just because it's 122 terabytes, right? It's like, think back to when hard disks used to be single sector, like one sector on a hard disk used to be 512 bytes.
Yep.
Well, technically today the sector still is, but the sector is just a construct at this point anymore, right? Because most hard drives for the past, now I'm really dating myself. When did advanced format come out? Like 15 years ago or something?
Yeah.
Right?
Too much overhead to deal with blocks that small.
Yeah, it just didn't make any sense to only have sectors be 512 bytes. So hard disks, at around the point of like the 2 or 3 terabyte Western Digital Red launch, I think is when they flipped that switch. They said, nope, that's it. All sectors physically are 4K now. And then that's kind of what has stuck. That's why most SSDs these days, they're all rated at 4K random. That all kind of was a carried forward thing from that advanced format decision on hard disks. That was happening back then around the same time that SSDs sort of came to fruition, right? But it just doesn't make any sense moving forward. Like, we're eventually going to get to a point where even a drive like this, that's a relatively small drive that was only 8 terabytes, maybe 16 terabytes, say 5 years in the future, probably isn't going to, still even stick to this 512 byte logical sector thing anymore.
Yeah, I mean, in terms of like testing with ZFS, 128K sector size, and by the time you get to the software level, I'm skipping a bunch of steps, but by the time you get to a software level, when you're dealing with, it's like, this is 122 terabyte volume or a 200 terabyte volume if you've got an array of these.
Right.
Your sector, it's going to be 128K. If you're doing an S3 like object storage, the object storage abstraction is not designed to deal with anything smaller really than 128K, 64K in some exceptions, and you're still well above the physical storage geometry that you're dealing with. So there's not as much overhead from that kind of thing as one might assume. Yeah,
and you've got, like, for ZFS, you could do record sizes.
Yeah.
But as far as when you make the pool, if you were to make a pool on a drive like this, you'd probably want to match the A shift, which is the resolution that ZFS is tracking blocks at the device level, right? Probably a shift of like 14 or 15 for this drive. So 14 being 16K.
Yeah.
Unless I'm doing my power math wrong or whatever in my head. But yeah, so you want to match it to roughly around the physical, in the case of this drive, it would be the page size of the NAND, right? Size. Now there's still all that stuff that goes on with NAND, which we don't need to go all the way down the rat hole, but like it's NAND is in blocks and pages, and it's almost like rewriting a CDRW back in the day, right? Like you can fill a block with new pages until you have completely filled the disk. And then you can do that with a whole bunch of disks, which would fit in here, a real whole bunch of, right? But eventually all the disks are now full.
Yeah.
And some of the data on some of the disks is stale data that you've already sort of overwritten somewhere else, like a new version of it, and you deleted the pointer to the old stuff. And eventually you have to pay the piper and you have to come back and go, okay, like everything's full. Now I got to go back and it almost, as from a NAND's perspective, it kind of feels like the manual process back in the day of, oh crap, that disk is full. I only want to change this one file. What do I got to do? And you literally have to read the whole CDRW back into the PC, actually get rid of the stuff that you didn't care about anymore and make your modifications and then write the entire thing back again, right? And that's where things get super painful. And that's actually the main reason why when you test any sort of data center SSDs, it's important to try to do it at a steady state performance level, because you don't really know how fast the drive's going to go until you've done that workload for long enough to actually have like sort of spread it across all of the media. Because almost any of these drives, this one included, it'll look way higher, it'll perform way better than any of those ratings that it's for. But eventually you will have lapped all of the NAND, and when you come right back around to the beginning, now things are going to, sort of level out to what they're supposed to do.
Yeah.
Right. Yeah. So that
some drives also have second or third tier aging where the media has gotten to a point and the controller is like, okay, I'm going to have to go just a little bit slower. And you usually see that in like year 2, year 3.
Well, there's
Depends
actually
on the rides.
There's a little bit of nuance to how that behavior works. So with a drive, so there's a PS1010, which is the 7.68 version, and there's also a PS1030, which is a 6.4 terabyte version. As if you opened them up and looked at the NAND, and even if you took apart all the die and desoldered them, and like it's the same amount of media is installed, right? It's still the same 8 terabytes of NAND that's in the drive. It's just that one of them only gives you so many sectors available, so much space available to use, and then the other one intentionally short strokes it even further. And so the end result is that as far as random writes to the drive, the 1030 would end up doing something like 2 to 3 times the IOPS compared to what this would level out at. Okay. Well, if you took this drive and you only filled it with 6.4 terabytes worth of stuff, it would perform basically like the 1030.
Yep.
Right? But the catch is that in that moment when you had only written, when you left 28% extra space available on the drive, the firmware and the management and everything that goes on in there would have evenly spread all that stuff out across all of the available blocks so that each block on average had about 28% pages that were discarded. And that's what makes it able to do higher IOPS, because everything's evenly spread out and there's just less of a chance that when you do a new write, you have to clear a block because there was, a lot more extra slack space available, right?
I know a lot of the audience is probably also wondering about, okay, so suppose the operating system does perfect management of trim and space management. It's like, that helps you a little bit, but that doesn't solve the problem entirely.
Correct. Yeah. All that's doing is letting the drive know, hey, I didn't need that stuff. And so the drive itself doesn't necessarily clear blocks just because it received trim, right? All it's doing is discarding those pages that it previously thought were valid data. Just because at the partition level, if you overwrote something at the partition level in place, the drive would know because you'd already allocated it once, and now you just wrote to the same LBA, the same address. You don't have to trim that, the drive knows. But if you went and deleted some files, there's no other mechanism to tell the SSD. So as far as the SSD knows, think back to old school data recovery, which you can't do anymore on SSDs because of trim, right? But when you deleted a file, old school, it wasn't actually deleted. That's why you could do undelete and all those other cool things back in the day, because the data was still sitting there. Well, now you have to let the SSD know, hey, I actually don't want that anymore.
That was a fun firmware bug on not a Solidigm drive where if enough sectors had been overwritten, it would lose track of the sectors that had been marked for trim.
Oh. That's a bad bug. Yeah.
Oops.
No. I mean, well, you didn't necessarily lose anything, though.
No, you don't lose anything.
You just the drive went way slower than it should have because it was trying to, it lost track of the things that it could have cleared from the FTL.
There's an option for trim on Linux to just be like trim all the sectors that are supposed to be empty, and it's like, okay, and it's like, wow, that's weird. This drive is now suddenly way faster than it was.
Yeah, it's just FS trim on Linux. Windows, believe it or not, will do trim. It's the defrag utility because, well, why? Yeah, sure, okay. That's where they put it. If defrag sees an SSD, it just issues trim when you try to tell it to defrag. And
what a fun existence.
It's weird. How did we get here from there? Sort of stuff. Yeah, that's where they put it. Okay, fine. Yeah. So let's see. What else is there?
What else is interesting about this 122 terabyte drive other than the insane capacity?
I mean, the capacity is pretty much the thing, right? You have these data centers that want power, space, and cooling, right? Like you only have so much space. Do you want to double the racks in your data center, or do you want to be able to do another upgrade cycle and just in place swap out drives? I'm sure that most people going to the 122 are probably not currently using our 61 terabyte drive, so they're probably getting way more than a double of their capacity for the given amount of rack space, and
better performance.
Although for a lot of these guys, that's why the 3 gig per second isn't even that big of a concern on this drive. I mean, yes, it's good to have the fast speeds, but again, the type of use case where you're going to have these, it's just going to be racks and racks full of them.
Yeah.
And in a lot of cases, you don't even have the bandwidth available to actually saturate the drives.
Yeah.
Because it's so wide of just a huge pool of storage.
Even at 400 gigabit, let's say you have a 400 gigabit storage network, one of the storage systems has 24 of these in it.
Right. You can't saturate them, even at 3 gig per second per drive.
Yeah.
Right. So, and even if you could, it's right on the line. So if your bottlenecks are reasonably matched, then I would just consider that a good pairing more than anything. Like you don't want to have a bunch of PS1010s that could write, 10 gigabytes per second in a rack and just to do mass storage. Like you're just at that point, and it's Gen 5 too. So at that point, you're just throwing away power at Gen 5. That's a good part of the reason why this drive still remains a Gen 4 drive, because yes, we could have engineered that to be Gen 5. It wouldn't have gained much because the QLC media tends to be more of a bottleneck and holds it back there, right? But we could have got more out of the reads, surely. It could have probably read at 14 gigabytes per second. That would have been great. It's just that, again, if you're installing them 24 at a time, what are you going to do with 14 gigabytes per second per drive in that case? It just doesn't make sense, right? So
122 terabytes in this form factor.
Yep.
How much time does mechanical storage have left? I'm sort of looking at this in LCDs versus CRTs because there was a good 10-year overlap there.
Yeah, I mean, okay.
There's already been 10 years of SSDs versus mechanical storage.
Cost per gig, hard drive's still king.
Yeah,
obviously. But yeah, we're starting to. It's always been this game since the very beginning. It's been a game of SSDs encroaching on hard disks, right? I mean, like back in the day, I had RAID 0 of 3 Velociraptors was my OS drive, and I went from that to a single X25M from Intel. That was that's what got me into the whole thing and started me on this whole crazy journey, right? And the drive was tiny; it was only 80 gigabytes.
But it was so fast. It was I'll deal with it.
So fast, it was just ridiculous, and so it made sense to justify the cost to get the performance difference, right? And so that's been sort of the way it has been encroaching into hard disks the whole time, right? Every time you go up another tier of I kind of want some capacity, but I'm really worried about the performance. And now it's getting to the point where, okay, well now you just do the capacity. As far as capacity in physical space, that's clearly the nails in the coffin on that one, right? With this thing. I mean, think of the volume of this compared to a 3.5-inch hard disk. I don't know, what's that, maybe 5 or 6 of these guys fits in the actual footprint, volume. So that's done and over with because you can almost get a petabyte worth of this in cubic inches
for me
compared to a hard disk, right?
For me, the really worrying thing is that the transfer rate for mechanical hard drives has basically flatlined, unless you cheat with multiple actuators or something like that.
Yeah.
Basically, every mechanical hard drive is on the order of 200-300 megabytes per second, whether it's 8 terabytes or 40, and that is a problem.
Right, and that starts to play into even things imagine you didn't even care about the performance. You didn't even care about the power, any of that other stuff, right? Put all that stuff to the side. If you thought of the process of hey, if a drive fails in your pool, how long does it take to resilver?
Yeah.
Right? And you're limited by, if you just replaced one drive, you're bound by the right bandwidth of just that one drive.
Yeah.
Well, good hard drive these days, 300 meg per second-ish. I mean, this is 10x that.
Yeah. It literally takes 3 days to resilver, assuming that the resilver is running at the fastest speed the drive could run at. Whereas
Right.
this at 122 terabytes, it's completed in under a day.
Yeah. So your rate of being able to swap, maintain your resiliency, your redundancy in the face of if there was a failure, right? And that's on top of the fact that these things are just more reliable than spinning disks.
Yep.
I mean, just SSDs in general, right? So there's a lot of compounding things that are just keep pushing the needle more towards like, okay, yeah. So it really is just down to the cost anymore. Like there's no all the other excuses are gone. It really is just like once, to the point where we probably start to see the hard disk like real true phase out thing happening. I don't think you actually have to fully cross over the price point. Like you just gotta get close because now you have so many other pros and on the side of the SSD that it's just like, okay, what are we even doing with the spinning disk of rust?
The spinning disk
Anymore.
industry has already been not healthy for a long time. They have not. I don't think anyone has posted a profit in quite a long time.
Well, yeah, because the margins have to be just razor thin there. I mean, the margins aren't super great on this side either. The margins are super thin as well. It's really just how much NAND can you cram into a box and sell it and try to make something off of it, right? And stay in business, just like anything else.
122 terabytes and 2.5 inches with good performance.
Yeah.
All things considered. Well, thanks for showing me, and it's been a fun chat.
Have fun playing with it.